like to welcome you all here today. Today we will have 3 sessions, 2 lessons and the GOM show. Erik sent by Slack the instruction to participate at the GOM show. Well, I'm the chair of the first lesson. I'm Pierluigi Graziani, and you already know the rules for questions, but I still want to remember them. In general, to ask a question, you should type Q in the chat. And to ask a follow-up on a question, you should type F in the chat. During the lecture, you will be able to ask clarificatory questions. With more substantive questions should be left for a Q&A session at the end. Well, the speaker on the agenda is Erik Curiel, and he will be talking about semi-classical gravity as effective field theory and the information loss paradox. Please, Erik, you have the floor.
Thank you. The title has changed.
Yes, it changed.
So we are today, in fact, finally going to talk about the information loss paradox. I am very pleased to say. And yeah, let's just jump right in and start eating our big, wonderful Italian dinner of information loss paradox. Okay. So just to lay out, just to tell you where we're going today, I'll be. Let's see. I think so. I think it was Sakshi who very rightfully said yesterday afternoon that the idea of information and information loss is at best ambiguous. I'll spend a little time talking about that just to start to get us in the mood, you know, the aperitivo, and then I'm going to spend a little bit of time talking in some detail about a very influential argument in the field that Don Rolf made first back in 2009. I mean, I can tell you one, an anecdote that I think really conveys how influential this argument can be. Ted Jacobson told me that it was this argument that convinced him to change his mind about unitarity. That before he thought that there was violation of unitarity in black hole evaporation, and after he learned of Don's argument, he was convinced to change his mind and decided that there is no unitarity loss. I think it's a very interesting, subtle, illuminating argument. I think in the end it doesn't quite work, and I'm going to explain why I think that, and why it doesn't work I think is also very illuminating. Like all really great arguments, even the ones that don't work, even when they don't work, they teach you something. But in order to explain that, we're going to have to spend a little time talking about yet more causality conditions, but I take it that everyone here is as pleased about that as I am, because the study of causal structure in relativistic spacetimes is one of the most beautiful fields of theoretical physics. So we should always treasure any opportunity to think more about it. Then I will in fact talk about the way that semi-classical gravity is, I think, most usefully thought of as an effective field theory. Although as Dan Harlow pointed out, I can't remember in which lecture, I think it was 2 lectures ago, that the way in which one can think of something like semi-classical theories, including gravity, as effective field theories doesn't quite fit the usual mold of effective field theory, either in condensed matter physics or in particle physics. So I'm going to say a little bit about I'll be talking mostly about how it might make sense to think of semi-classical gravity as an effective field theory. And in any event, no matter how I think one really tries to make that idea cogent, I think doing so has very profound implications for our understanding of the information loss paradox. And then I'll finish, hopefully conclude, actually make it through the lecture this time, by just some general synoptic valedictory remarks about the epistemic situation we find ourselves in today with regard to gravity and quantum theory. Okay, so I think the most important fact about the context in which the evolution paradox, the information loss paradox is formulated, is that there are two different notions of dynamical evolution that are in play. The first one comes from quantum field theory. We have a quantum state that's of a quantum field that's defined on a Cauchy slice in a relativistic space-time. Recall, a Cauchy slice can be thought of as something like all of space at a given moment of time. It's the closest analog we have in general relativity to that Newtonian idea. And most importantly for our purposes, Cauchy slices are the proper geometric objects that one uses for solving initial value problems. So if you impose initial data on a Cauchy slice and you then evolve it forward to recover the dynamical evolution of your system. So in this case, what QFT tells us is fix the quantum state and then on your Cauchy slice, and then evolve it forward using Schrodinger unitary evolution. And if you're wondering why I have quotation marks around the kind of definition of the unitary operator, it's because the Hamiltonian operator is very rarely well defined in a mathematical sense in these contexts. It's it's well defined as physics math, but it's not well defined as real math. So just the scare quotes just remind us of that. But there's a different notion of evolution in play here as well. The notion of evolution, dynamical evolution, we get in general relativity. And here, once again, instead of fixing the quantum state on the Cauchy slice, we rather fix initial data appropriate for the Einstein field equation. That consists of a positive definite Riemannian metric on the Cauchy slice, which you should think of as the full 4-dimensional Lorentz metric restricted to the 3-dimensional space-like surface. And the other part of the initial data, which one can think of as, if this is configuration, if you think of this as a Hamiltonian problem, this is the 3 metric is configuration, and the conjugate momentum is the extrinsic curvature of the Cauchy slice. Don't worry if you don't quite know what that means. What's important to know is that these two objects encode all relevant geometrical information about the Cauchy slice, and it tells the Einstein field equation how to evolve it forward to recover all the geometry of space-time. And that sense of evolution is often called Cauchy development. So we have two senses of evolution here in play. And it's not It's not entirely clear how these two fit together or whether indeed they do. In fact, one might have thought the central issue of the information loss paradox would standardly be posed as something like, are these two notions of evolution in an appropriate sense consistent with each other? In fact, it's never posed like that, because to address that question would require being able to solve the semi-classical Einstein field equation in some generality, and we're just not able to do that. So I think this is probably not the only reason why I think physicists and philosophers don't think about the problem in this way. But I think it is one important reason why we don't think about the problem in this way. I personally think this is the heart of the issue, but it's too hard of a problem for us to attack directly. So we attack it indirectly by posing one of the 4 following questions. So I claim that if you look at the literature, at the voluminous, vast, thermodynamical, approaching thermodynamical limit amount of literature on the information loss paradox, almost all the ways, whenever people are being even a little bit careful and they actually tell you what they mean by the information loss paradox, they almost always, like, except maybe a set of measure zero, they mean one of these four things. And they usually, unfortunately, it's very rare for them to have any kind of a recognition or self-awareness that that what they are asking and proposing is a question different from what other people pose. So, and I claim that none of the four of these are in any clear sense equivalent to each other, to any of the others. And none of the four of these is in any clear sense equivalent to the question about the consistency of two different kinds of evolutions that I mentioned before. So the four of them are, first, I call it the Hawking problem because it is the problem that he posed in the 1975 paper. Is there a unitary scattering matrix from past null infinity to future null infinity? So if I fix initial data for the quantum field and for the geometry of space-time in the distant past, and then use and then try to use normal scattering matrix methods so that I can ignore the fine details of interactions in the interior, but just try to solve for the final resulting state asymptotically far away. Can I model that process by a unitary scattering matrix? And his answer at the time, infamously, was no, we can't. There's what I call the page curve problem. I think Wallace calls it the page time problem. And the reason I don't like calling it the page time problem is because if you think about real black holes, there is no such thing as a single page time. Real black holes are constantly having stuff fall into it and their mass is changing. So what one means by the page, so it's only in super idealized situations for black holes that are isolated for their entire evolution that one has a well-defined page time. But the page curve is always well-defined. Does the entropy, so this problem is essentially, does the entropy of Hawking radiation decrease at late times during evaporation? There's what I call the final state problem. This is the one that this is probably the one that most people posed and talked about up until at least the early to mid noughties when holography started taking over. Is Hawking radiation in a pure state after evaporation ends? Then there's what I call the recovery problem. Can the information encoded in a physical system be recovered after it enters a black hole? I mean, they all have more or less vaguely to do with the idea of unitarity, some more explicitly than others. And they all have more or less vaguely to do with whether one can hold on to the principle of unitary evolution in quantum field theory for systems that include an evaporating black hole. But this is all, but also complicated by the fact that in scattering theory in particular, and in particle physics in general, the word unitarity has two completely different meanings. And again, most physicists are very careless in their usage. And again, that's not a criticism. That's the way physics operates. If they try to behave like philosophers all the time and be super precise, and that they would never make any progress. But we as philosophers, and I'm including all the young physicists in the audience today, because you are honorary philosophers during at least this lecture. This is all complicated by the fact that in scattering theory, particle physics, the word unitarity really has two meanings. One is conservation of probability, and the other is evolution from pure states to pure states. And those two they're neither mathematically nor physically nor conceptually equivalent to each other. One can have conservation of probability with non-unitary matrices. Technically speaking, if an evolution operator is merely regular and normal, those are technical conditions one imposes on a self-adjoint operator on a Hilbert space. One uses that instead of a real unitary operator, one still gets conservation of probability. Probability as calculated by the Born rule. And so that is completely, but it's also the case that those kinds of operators do not take pure states to pure states. It's also the case that, that there are more general Lindblad type of evolutions that one uses for so-called open quantum systems. So quantum systems that one explicitly conceives of and models as being coupled to some kind of a coarse-grained or dissipative environment. And the evolution operator for those quantum systems are not unitary, but one still has conservation of probability. So, this ambiguity comes out most clearly in the standard argument about the Hawking problem, and its relative, the final state problem. So just to get clear on, to have something to focus on, and also because it's going to be relevant in the conclusion I have about Merolf's argument. Let's focus for the moment on the final state problem. And again, as I claim that at least for a very long time in the literature, this was the most common way of posing the problem. And it's still one of the most common ways people talk and think about it. So the final state problem is most naturally, is most easily, I think, just grasped by visualization with a nice space-time, a nice Penrose diagram. So this is one of the standard Penrose diagrams for a generic evaporating black hole space-time. We have the collapsing ball of matter. Once it collapses inside a Schwarzschild radius, the event horizon forms. And recall that, as I mentioned in the very first lecture, one has to be careful in reading Penrose diagrams because Penrose diagrams are designed to make causal structure perspicuous, but they do that at the cost of wildly distorting space-time volumes. So even though it naively looks like the area behind the black hole is increasing and increasing, in fact, exactly the opposite is happening. The space-time volume is shrinking and shrinking and shrinking until it approaches zero volume as you approach the singularity. And so the black hole is shrinking and evaporating. And at this point, the black hole has completely evaporated, whatever exactly that might mean. And so in particular, the Hawking radiation, you can think of the Hawking radiation has been traveling, let's think of it as all massless scalar fields, just to be easy. So it in a sense, travels along null geodesics. So the Hawking radiation is traveling along these null geodesics, heading out to future null infinity, where observers measure its temperature and get the standard Hawking temperature. But notice that this little region, whatever exactly happens here, it's visible to future null infinity. So observers asymptotically far away can see whatever exactly happens at the end of evaporation. On the standard picture, whatever happens is disruptive enough that, in fact, the causal structure of space-time changes. Here, so this is space-like infinity. So every single Cauchy slice, which is basically think of as a space-like surface, they all extend out to space-like infinity. So here we have one achronal complete slice in space-time, and it is in fact a Cauchy slice for its past. If you specify initial data on it and evolve backwards in either the Schrodinger sense or the Cauchy development sense, one gets a well-defined backward initial value problem, dynamical evolution problem. But it's not a well-defined, it's not a Cauchy slice for future. Because here, for instance, sometime like, recall one of the defining characteristics of a Cauchy slice is that every single causal curve in space-time intersects it exactly once. To be more precise, every single time-like curve in space-time intersects it exactly once. One has to be a little careful about the null curves, but that's not important for our purposes. Here is a time-like curve that doesn't intersect this surface. It starts right here, passes through this surface and reaches all the way out to future null infinity. So whatever determines the evolution of stuff on this curve, it's not fixed by what happens here. Because nothing here can send a causal signal to where this curve started, so to speak. So if you think about the state of the quantum field on this surface, where by assumption it's a pure state, but what we normally think about the Hawking radiation, what we normally think about is the state of the field outside the event horizon. And we get that by tracing out all the degrees of freedom inside the event horizon. And so just by standard rules of quantum mechanics, when we have a pure state and we trace out the degrees of freedom of some subsystem of it, we end up with a mixed state, a density operator. So the state on this part of the surface is restricted to this part of the surface is a density operator, it's a mixed state. Notice it's only information that's on here that can register up here. This is another, all of space at a given moment of time, or the closest analog of that up here to the future of evaporation. In other words, all the information of the pure state cannot reach up here. Only the information from the mixed state can reach up here. So the state of the quantum field up here must also be a mixed state. And there's no further, part of the system left to tensor, to untrace, to purify, to make it into a pure state. So this is the state of the whole quantum field at that quote unquote moment of time. So we have, it looks like, a pure state that has evolved into a mixed state. Now, just to summarize, by Cauchy evolution, just by looking at the causal relations, the possible causal relations between the two surfaces, a pure state on sigma 1, the lower slice, develops into a mixed state on sigma 2, the future slice. By Schrödinger evolution, this cannot happen. That's the final state problem in a nutshell. The root of the conflict, I claim, lies in the pathology of the causal structure of the space-time. Sigma 1 is a Cauchy surface for that part of the space-time lying beneath the null surface, connecting the evaporation point to future null infinity. So in fact, if you were to continue this null line, this null surface up to future null infinity, so think about all of space-time up to and including the part that is behind this surface. So everything from here downward. If you think of that as just its own space-time, ignore everything else, that is in fact a globally hyperbolic space-time, and this is in fact a real Cauchy slice for it. It's only what happens to the future of this surface that is not determined by what happens down here. And so, as I said, the future slice sigma 2 can at most know about the information encoded in the mixed state defined on sigma 1 by tracing out that part of the state associated with a part of sigma 1 lying behind the event horizon. Okay, now that we have that picture of the final state problem in mind, let's look at Morolf's boundary unitarity argument. Now, as I remarked already, it was a completely novel kind of argument when he developed it. It's widely influential. And it comes to the conclusion that black hole evaporation is fundamentally a unitary process. I think it's really super clever and cool and delivers real insight on a number of issues. But I also think it begs a fundamental question in the same way that all arguments that are holographic in flavor, and his is, even though it's now called Morolf's boundary unitarity argument, the name of the original paper was holography argument. I mean, I think it begs a fundamental question, and it does so in a way, in I think all holographic kinds of arguments I know of beg this question. But I really like Morolf's argument for lots of reasons, one of which is it's such a really crisp, clear, kind of really simple, just amazingly simple, conceptually simple argument that it really brings out this problem that I want to point to, that I think is a problem, with real clarity. And because just, since I've already told you I don't think the argument works, and so to try and prove to you, try to reassure you that I'm not going to be setting up a straw man, I'm not going to be distorting anything seriously in the argument, I'm actually not going to use slides that I wrote to present the argument. Aaron Wall, I'm going to use some slides from Aaron Wall from a talk he gave in 2019 in which he gave an exposition of the argument and defended it. Because Aaron, in fact, really thinks the argument works and vigorously defends the validity of the argument. So I'm going to present to you what I take to be, one of the strongest ways of presenting the argument in the voice of someone who thinks it works. Okay. So assume that we are in some asymptotically ADS spacetime. And here, in fact, is the Escher is the kind of Escher picture that Dan was talking about yesterday that gives a picture of the geometry of a spatial slice in an ADS spacetime. So as you move outward from the center, there are in fact an infinite number of little birds that you will pass through. But since they're shrinking quickly enough that even though there's an infinite number of them, it takes only a finite distance to cross over all of them. That's one of the hallmarks of a spacetime, of a geometry that is everywhere negatively curved. And even though we're in asymptotically ADS, we are not assuming ADS CFT. In fact, as Aaron says, we are going to be proving something like ADS CFT. So the argument concerns, this little green strip is supposed to be a region on the boundary at asymptotic infinity. And the argument concerns the set of quantities that are measurable on the boundary at some given time t. So this is the boundary at some time t as defined by what happens in the bulk. And Aaron is not going to think of the boundary as being perfectly space-like, but it's going to include a little bit of temporal thickness. And that's only to avoid some certain technical problems that are involved when you really try to make this argument precise and do all the calculations correctly. One, as always in quantum field theory, one has to smear some of the operators, but that's only a technical problem. It's not relevant to the conceptual part at all. I just mentioned it for completeness since Aaron mentions it, but you don't have to worry about it at all for the rest of the argument. And now the claim is basic principles of physics will now imply that the info that falls into a black hole in the interior remains always accessible to observers measuring things on the boundary. No information loss. So Aaron will present the argument by giving 4 axioms that characterize the behavior of this physical system, space-time plus fields in bulk on boundary. So these are axioms that specify the behavior of the system on the boundary. So we have in this little strip on the boundary, we have an algebra of operators. Curly A is an algebra of regular quantum field theory operators. So it's a vector subset of operators in a global Hilbert space. It's closed under addition. That's what it means to be a vector space. It's closed under multiplication. That's what it means to be an algebra. It includes it is complete with regard to taking reasonable limits and in various well-behaved physically relevant topologies. So it's actually a C-star algebra. These are all standard assumptions, completely standard assumptions in algebraic quantum field theory when describing the set of all measurable quantities in a region. Nothing problematic or weird or suspicious about this at all. Axiom 2, the Hamiltonian is measurable at the boundary. And this is in fact, something that we expect from general relativity. The Hamiltonian in this case should be the ADM mass that's defined at asymptotic infinity. The Hamiltonian is just an ordinary, when thinking about it as being associated with the stress energy content of a quantum field, it's just going to be the Hamiltonian operator So what we mean by saying it's measurable mathematically, that means the operator that represents it is in our algebra of observables. And as Aaron remarks, it's not just general relativity in which the energy, the Hamiltonian, is defined on the boundary. In fact, this is true for any diffeomorphism invariant theory of gravity. The total energy is just a pure boundary term. So gauge symmetry implies that the Hamiltonian equals 0 locally up to a total derivative that arises when the diffeomorphism vector that one is dealing with doesn't vanish on the boundary. And the ADM energy, the Hamiltonian, is obtained from the case where this the vector that generates the diffeomorphism is a time translation on the boundary. Again, nothing problematic about this. Completely straightforward. If one has to assume anything, this seems like exactly the right thing to assume. Axiom 3, the Hamiltonian generates time translations. Again, it's absolutely straightforward thing you get in standard and quantum mechanics. So the Hamiltonian is a self-adjoint operator and we're just for various convenience, we're working in the Heisenberg picture. So we talk about the time translation of operators rather than the time translation of states. Again, no problem whatsoever, nothing suspicious, nothing sneaky, totally standard. And as Aaron says, these rules are just simply the definition of the Hamiltonian. This is what you mean in quantum mechanics by the Hamiltonian. So if the ADM mass is going to be the Hamiltonian, this is what it has to do. And again, there's nothing suspicious or weird about this. And I don't exactly agree with Aaron on this parenthetical remark. He says the identification of this with the previous H, the one defined by the ADM mass, is related to the exact equivalence of gravitational and inertial energy in GR. The reason why I don't completely agree with that is because of some subtleties that have to do with defining what one means by gravitational and inertial energy in GR. But at the level of approximation we're talking about, I think it's not a problematic statement and certainly doesn't bear in any way on the cogency or possible validity of this argument. Axioms 1 through 3 imply that the boundary evolves unitarily. So here is a section of the boundary. It's time-like. Here are two little, slices, little smeared out spatial slices on the boundary with their associated algebras of observables. So an observer at this moment of time on the boundary, all the measurements that she makes, all the observables she has accessible to her are in this algebra. A little bit later on the boundary, when she's here, and she's making measurements and thinking about what observables are accessible to her, all of those are in this algebra defined, associated with that little region. And axioms 1 through 3 do imply, and this is mathematically correct, physically what you expect, that if OT is a family of operators related by time translation symmetry, i.e. there's you take some family of operators here and you push them forward by the Hamiltonian evolution. You dynamically evolve them from this time to that time. This is just the standard quantum definition of doing that. Then what that means is that anything that you can measure here at one time is also and recover information about, you can measure and recover information about.
Sorry, Erik, there is a question by Vincenzo.
Yes, please.
Erik, in a couple of slides before, you said that H is O on the border because gauge invariance, but I was not able to understand why.
Hold on one second. I'm trying to, there. Okay. So when there is, so by diffeomorphism invariance, so if you calculate H should be, H is computed in a certain way by taking integrals in the interior over all contributions to stress energy to mass. And it turns out that diffeomorphism invariance implies that that integral should be 0, except for whatever contribution the boundary makes. So you can think of this as exactly like, it's exactly like Gauss's law, the electromagnetic field. I think that's the right way to think about it.
Many thanks.
Does that help?
Yes, it's helpful. Thank you.
Okay. So again, here we now have axioms 1 through 3. They imply that anything that's measurable and you can recover information about here just by straightforward rules of time translation, symmetries, and quantum field theories is measurable, and information is recoverable at a later time here. In other words, it just follows from the axioms we've listed that no information can be lost from the boundary, unless, of course, it was never on the boundary. But that's, I mean, logically speaking, that still doesn't mean it can be lost on the boundary. But you know what Aaron's trying to say. Any information that's on the boundary is never lost. Now we get to axiom 4. That is going to be the one relevant for connecting what we just did to the issue of black hole evaporation. Axiom 4. There are other non-trivial operators in the algebra on the boundary that can be excited to form a black hole in the interior. And this axiom is motivated by and justified by the idea that we are doing quantum field theory in a relativistic spacetime. You expect, and we're doing it in ADS in particular. So remember, even though the boundary is infinitely far away, it takes only a finite amount of proper time for causal signals from the interior to reach the boundary and to bounce off and go back into the interior, because of the negative curve, because of the way the negative curvature of the geometry works. In other words, if I perform some physical operation here on the boundary, and that physical operation creates, some kind of radiation that has non-trivial stress energy, that radiation of non-trivial stress energy should propagate into the interior of the space-time. That seems perfectly physically reasonable, again. And so, in other words, if we're considering a quantum field in the interior that's just a scalar field phi, I should be able, it just makes physical sense that I should be able to do things to phi. I should be able to hit it with a stick, figuratively speaking. Change its value, make changes that causally propagate back into the interior. Technically, what this means is that we have a sideways Cauchy problem. Now, instead of having an initial value problem where the initial values are posed on space-like surface and evolve forward in time, we're now posing initial data on a time-like surface and evolving that forward in time. It's actually quite mathematically subtle. And Aaron says basically okay. I'm not going to go into the mathematical details of that. It's really rather arduous. And he says, I mean, to motivate again how really physically trivial it seems like this assumption is. He says, I think completely rightly, no, we just need some non-trivial field operator, phi operator out here, because on some small boundary interval. Because as long as we have that, we can just keep on iterating it and iterating it and iterating it and generating, just massive amounts of stress energy to send in the interior, enough so that it should eventually, we can send enough so that it'll condense and collapse into a black hole. Therefore, now we conclude, information is not lost when it passes into the black hole. Why is that? Excite the fields at T with the boundary operators that act on the field. So we send in a big pulse of stress energy that since it's massless, it travels along these null lines, these null geodesics. It's massive enough that as it travels in and is collapsing on itself because of its own self-gravity, eventually it collapses inside of its own Schwarzschild radius, an event horizon forms, singularity to the future. All this stuff is lost inside the black hole, so we think. Whatever happens by the event horizon is now unknowable to us. We can't recover information about it. That's how the normal story goes. But Morozov has now shown us that can't be true. In fact, at any later moment of time T2, right here, even before the black hole evaporates, the information that is back here, that is behind the event horizon, is still available on the boundary in principle and can be measured by some complicated experiment. And that follows directly from this fact. Any information here is available here. So all the information, all the information that I used to generate this pulse and send it to the black hole, that's information I had here. Therefore, it is in principle, I can recover that information here. Therefore, information can't be lost. Therefore, black hole evolution must be unitary. So let's summarize the assumptions. We have an algebra of operators at every moment of time on the boundary. We have the ADM mass, which we are going to assume unproblematically is the Hamiltonian operator in this algebra of observables. H is self-adjoint. H induces time translation by standard Heisenberg picture quantum mechanics. There exist non-trivial operators in the algebra on the boundary that we can use to manipulate the boundary values of the field and can be used to form black holes in the interior. All seemingly completely reasonable, unproblematic assumptions. And yet I claim something goes wrong. Just to tell you where I'm heading, this I think is the problematic assumption. This I think is the problematic assumption. There's a sense in which Aaron is completely right. It would be shocking if he weren't. He's like one of the most naturally talented and gifted theoretical physicists of his generation. He's extraordinary. So if he were wrong, just wrong about something as basic as this, it would be just truly shocking. So there's a sense in which he's not wrong about this as a technical mathematical problem. My issue with this is that there's an implicit assumption in this claim about the causal structure of the interior of spacetime. And I'll try to make that clear. But of course, to do that, we have to talk about some more causality conditions. Okay, as I was saying, the nub of my problem with Morozov's argument is that it implicitly assumes the interior of spacetime is causally well behaved. All required actions on the boundary can propagate in a determinable way anywhere into the interior spacetime I want. But recall the final state problem. The final state problem suggests that this is exactly, in fact, what is at issue, whether spacetime is causally well behaved in this sense. And so to make this claim precise, make my claim precise, that Morozov's argument relies on an implicit assumption that is exactly what is brought into question by the final state problem. Pardon me. I'm not a normal smoker, but going out with friends, birthday, have a few beers, ended up smoking some cigarettes last night. You have to engage in some vices on your birthday, but now I'm paying the price. So to make the claim precise, I will introduce a few more causality conditions and a theorem by Martin Lesord, and show where in Morozov's argument that try to make clear where in Morozov's argument the implicit assumption is made, I think without justification. Okay, so now I'm just going to give you some more definitions of causal conditions. So just assume some anti-relativistic spacetime. We say this spacetime is distinguishing if it is the case that for all points, if the causal past of the chronological past of the 2 points are the same, or the chronological future of 2 points are the same, implies that they are the same point. So in other words, 2 points can't entirely agree on what happens in their futures, and they can't entirely agree on what happens in their pasts unless they are the same point. That may sound like that. It may sound as though that would be impossible not to happen, but I'll show you an example of a spacetime in which this fails in a moment. So we say a spacetime is reflecting if for all points, if it is the case that the past of one of the points is entirely contained within the past of another point. And remember, on the first lecture, when I defined the chronological futures and past of points, and I remarked that it's a highly non-trivial fact, it's a deep fact about the chronological sets, that the future and the past of a point are always topologically open. What that means is that it is always the case that if point Q is to the future of point P, it is always true that the future of Q is contained in the future of P. So this first condition is always true, and same thing for past. Mutatis mutandis. This is always, so whenever P is to the chronological past of Q, this statement is always true. That's true. That's kind of trivial. But what reflecting says is, if that is true, then it's true that the future of Q is contained in the future of P. And again, it may sound as though it's completely impossible that this could fail, but it can, and I'll show you an example in a moment. And now the really important condition that we need for Martin's theorem is causal continuity. If a spacetime is both distinguishing and reflecting, then we say it's causally continuous. And I'll show you a picture of a spacetime that fails to be causally continuous, and that will give you a kind of I think will give you a very strong intuitive feeling for what the condition means. I can tell you right now, very crudely, what it means is, if you look at 2 points, spacetime points that are very close to each other, their chronological pasts should look almost the same. They should look almost identical. Moving from one point to a very nearby point shouldn't make radical changes to the chronological past. So it shouldn't be the case that making very, very, very small changes to my position in space-time shouldn't radically change what can causally influence me. Shouldn't radically change what I can observe has happened in the past. So here's a space-time that fails to be distinguishing to the future. So it's a torus, or I guess actually it's more precisely it's not a torus, it's a sphere. Sorry, I mean it's a cylinder. God, I'm a little fuzzy today. Okay, so we're identifying these two sides. So it's just a cylinder. The null cones, are pointed up in a kind of normal way. As you go forward in time, they start tipping over and tipping over until you reach this line. And since this line is tangent to all the null cones, this is a null geodesic. So this would be a closed null geodesic. This would violate causality, except we're removing from the spacetime this little strip, and that includes a point that would have been on this line. So this, in fact, is not a closed null geodesic. There's a little break there. So it's not a closed causal curve. But what that means is that, so if you look at the future of point P, the future of point P includes everything above that line. But the future of point Q also includes everything above that line. So the futures of point P and point Q agree, they're identical. So it's not, the spacetime is not distinguishing to the future. It is distinguishing to the past, because every point back here has different, every point back here has different past and futures because of this little strip that we removed. Here's a space-time that is not reflecting. So we've removed, just think of this as two-dimensional Makovsky space-time. Don't worry about that this is something else they were talking about. So we removed this little wedge from two-dimensional Minkowski spacetime. Then it is the case that X is in the future of Y. So the future of Y is everything that is inside this, everything you can reach, so that the null geodesic emanating from Y over here just ends there because we've removed those points in the space-time. But you can go up to the future and then cruise along this null geodesic well, it does not be H. So let's say it's a little point over here, some point right there. So I can reach that point from Y by going like this. And so the entire future of this point is included in the future of Y. But this point, the past of this point, includes points down here that are not in the past of Y. So this spacetime is not reflecting. And now here's an example of a spacetime that fails to be causally continuous. This is just two-dimensional Minkowski spacetime. We've removed this space-like surface. We just excised it remove these points in the spacetime manifold. P and Q are points that are very close together. The past of P is very truncated. It just stops there. The only causal signals that are reachable from at P are ones that are generated in this tiny little area. The past of Q is much bigger and looks very different. Every single point back in here is in the past of Q and can causally influence Q. So this spacetime is causally discontinuous. Now we can state Martin's theorem. Let a spacetime be chronological.
Sorry, Erik.
Yes.
Nicolo
Yes.
has a question for you.
Yes, please.
Hi, Erik. 2 slides before, you probably, if I don't understand it, you said that space-time, the previous slide, you said that space-time didn't distinguish past and future, future and present, or something like that.
It's not. Yeah, I'm sorry. Go on.
But distinguish the past. My question is, that is a sort of presentism for present and future, but without past, or something like that?
The condition as a mathematical condition on the geometry of spacetime and as one with a physical interpretation, I claim is completely neutral with regard to those kinds of metaphysical questions. This condition makes sense. You can describe it what it means physically, irrespective of whether you're a presentist or an eternalist or some other ist I don't know about. It the physics is completely independent of the metaphysics here.
Okay.
All this means, what it means that it's not future distinguishing is take any point to the, so I claim that the future of P is identical to the future of Q. What that means is any point I can reach by drawing a time-like curve from P, say that point right there, I can also reach by drawing a time-like curve from Q. Since I can do that here because I draw this curve It's this point right there. But remember, I've identified the boundaries. This is a cylinder. So going there just really wraps around and comes back here and reaches that point.
Okay.
So every single point to the chronological future of this line is contained in the future of P and in the future of Q. And those are the only points contained in the future of P and the future of Q. Therefore, the future of P and the future of Q are identical. They're the same set.
Okay, thank you so much.
Even though they're different points. So whether you think that these points in the future don't metaphysically exist until some causal signal reaches them or something like that, or whether you think they always exist because you're internalist, doesn't matter.
Okay. Yeah.
You can describe physically what this means without making any assumptions about what kind of existence space-time points and futures and past may have metaphysically.
Okay, thank you so much.
Sure. Okay. So let script M be a chronological space-time. So that means it has no closed time-like curves. It has a time-like asymptotic boundary. Its future null infinity is time-like, exactly as in Rolf's argument. It's time-like. We're just going to assume that the time-like asymptotic boundary, the future null infinity, has the topology V cross R, where V is some fixed topological space. In Rolf's example, it's a circle cross R. And we're assuming that there is a non-trivial black hole region and event horizon. I'm not going to spell that out because you now know what that means in all the fancy symbols and language. And also it's the case that the boundary of past null infinity, the boundary of the chronological past of future null infinity, in other words, the event horizon, is contained in the topological closure of the chronological past of some sigma, where sigma is a complete cross-section of future null infinity, i.e. a space-like submanifold of future null infinity with this topology. Under these two assumptions, M is causally discontinuous. And so I'll first show you a picture. So this condition may sound a little complex, and it is, but it has a very simple and straightforward physical interpretation. It captures the idea that the event horizon persists only up to a finite moment of time in the interior of a spacetime, up to a finite moment of time as measured on the boundary, i.e. the black hole evaporates. So I slightly altered the phrasing of the original statement of Martin's theorem just to make it more perspicuous how it applies directly to Rolf's argument. But I claim that, in fact, I've actually slightly weakened it, but Martin's original theorem implies my statement of it. So I'll show you a picture of what this condition means. So again, let's look back to the space-time that illustrates the final state problem. And this is a space-time that satisfies the conditions of Martin's theorem. So let's find the boundary of the chronological past to future null infinity. So here's future null infinity. Here's its chronological past. Its chronological past doesn't contain any of those points. So this is the boundary. The boundary is just the event horizon. Whoops. Now let's consider the closure. Let's take a little cross section of future null infinity, a moment in time on future null infinity. Consider its chronological past and take the topological closure. So let's in fact take that moment of time right there on the boundary. Its chronological past isn't the whole space-time because it doesn't include these points up here. That's the future. But it does include everything down here. It does include everything in this diagonal strip. It, of course, still doesn't include points behind the event horizon. But if you take the topological closure, and it doesn't include the event horizon itself, because the chronological past, remember, is an open set. So if you take the topological closure of it, you are now including this boundary. And this boundary is contained, but the topological closure of the chronological past now contains more than this, because these points up here are not in the chronological past to this point. So the chronological past to this point, the boundary of it also includes this null surface here. And so it's now clear the event horizon is a proper subset of the entire boundary of the chronological past of this region of future null infinity. So now recall this crucial step in Merle's argument. This is the one I already told you that I'm finding a little problematic. That the sideways Cauchy problem is basically okay. That means that it's always the case that I can arrange it that by messing around with the field, on the boundary, by manipulating it, which is represented in quantum mechanics by acting on it with self-adjoint operators. By doing that, I can always arrange for causal signals to be sent anywhere in the space-time I want, foreign black holes anywhere in the space-time I want. But that assumes that the interior of the space-time is causally well behaved. That is to say, assuming that the interior is not, for instance, causally discontinuous because a black hole has badly evaporated. And to show you really, I hope very vividly why there is this implicit assumption. Let's say that we've done this. We've manipulated the field, sent in this massive burst of stress energy that's collapsed. That's because of its self-gravity is collapsing on itself until it eventually passes within its own Schwarzschild radius and the event horizon forms. And now a little bit later, we do the same thing, but we do it with a little bit less bit of stress energy. So it's going to take longer for it to fall within its own Schwarzschild radius. So it actually collapses and forms its own black hole inside the original black hole. According to Morel's argument, there's nothing problematic about that. And we can just keep on doing that. We can just keep on sending energy in and making ever smaller black holes inside the original black hole as often as we want, right up until we reach, as close to the evaporation region as we want. I claim, though, that the capacity for us to be able to do that is exactly brought into question by the fact that if it is the case that that a black hole evaporation ends badly, we in fact won't be able to do that, because at these points up here, because if we were able to do that, then all the information that was contained in the little black holes that shrunk and evaporated behind the evaporation point of this guy. So we have all these little black holes that we created are evaporating behind the original event horizon because they're really small, so they evaporate really quickly. So all the black holes that evaporated behind this evaporation point, the claim is all that information should be accessible up there, and it should be recoverable. But if the space-time is causally discontinuous here, then in principle that would seem to be a violation of the fundamental causal structure of our space-time. That information that was in black holes that evaporated already behind this evaporation event would be accessible up there. And you can't reject this problem, I claim, by saying, well, we don't really know what happens at evaporation points. We don't know really if information is lost, if things are causally discontinuous. We would need a full theory of quantum gravity to know that. So we can just, but the strength of Martin's theorem is that the claim isn't that the causal discontinuity is restricted to a region out near the evaporation point. The causal discontinuity is visible arbitrarily far away. the causal discontinuity is visible at future null infinity. The causal discontinuity doesn't care what happens in a neighborhood around the evaporation point. The neighborhood around the evaporation point can be, the geometry of the neighborhood of a neighborhood of the evaporation point can be anything. Anything quantum gravity tells you it can be doesn't matter. As long as it's the case that there is a little, that's far enough away, so fine, quantum gravity takes over there. Who knows what really happens? Doesn't matter for Martin's theorem. Because there's always gonna be a little neighborhood around here that is where we're far enough away from the quantum gravity region that is going to look classical, and but that is all you need, because the points up here, that neighborhood is still causally discontinuous. As I move from here to here, what I see in my chronological past radically changes. So that what I have given you, by the way, is not yet a proof that Morolf's argument is wrong. What I have given you is a reason to doubt its validity. In order to prove that Morolf's argument is wrong, I would have to do something like prove the following conjecture: Schrödinger evolution is impossible in a causally discontinuous space-time. But that obviously is not a mathematically precise statement. So I don't yet know what it would mean to prove this. But I think that in fact it's possible to turn this into a mathematically precise statement amenable to proof. And moreover, I think it's true once you give the proper mathematical formulation of it. If that's true, then Morolf's argument can't be right. At least Morolf's argument is incomplete. I think is a fairer and a more precise way of saying it. Morolf still owes us a reason for assuming that the interior of his spacetime is not causally discontinuous, even though the final state argument suggests it is. And I've argued that Martin's theorem suggests it is. And I've argued that the physical application of Martin's theorem to the context of Don's argument doesn't depend on the details of what quantum gravity tells us happens very, very near the evaporation point. Okay, and I claim that exactly that same problem infects every single holography argument I know of in favor of unitarity. Okay, so now let's talk about the fact that semi-classical gravity is, at the end of the day, it is, in some sense or other, an effective field theory. Deal with it. Let's try and deal with it. So recall that Hawking, as I argued in the previous lecture, since Hawking radiation is not generated by the microdegrees of freedom of the event horizon itself, it's not blackbody radiation in the standard sense. And as I argued, this generates what I shall call the temperature decoupling problem. Why should we believe the thermal temperature of Hawking radiation is the, I guess I should say, the thermodynamical temperature of the black hole, when the Hawking radiation is not generated by the microdegrees of freedom of the event horizon? So recall, it's when you have your glowing lump of hot iron. The reason why we think the blackbody radiation is the temperature of the blackbody radiation is a direct proxy for the statistical thermophysics temperature of the iron is because the micro constituents of the iron, their jiggling and wiggling of the electrons and atoms, is what generated the blackbody radiation. So the jiggling and the wiggling, which is just the temperature of the iron, is directly encoded in the power spectrum of the blackbody radiation of the iron. That is not what happens at all in Hawking radiation. Why do we believe this? Why do we believe that the temperature of the Hawking radiation is the temperature of the black hole? I'm not, by the way, claiming that it's not. I'm just claiming that so far, that a further step needs to be made in order to really make that claim really deeply warranted. In order to make the claim warranted that the temperature of the Hawking radiation is the thermal temperature of the black hole, one needs some further assumption to bring these two prima facie disparate phenomena. On the one hand, the presumed microdynamics of the horizon, whatever that is, some quantum gravity stuff. And on the other hand, the microdynamics of the external quantum field on the other, the excited Hawking modes. One needs some further assumption to bring these two things into a kind of explicit and harmonious relation with each other to make sure that they really are causally related in the right way, to make the thermal power spectrum of the Hawking radiation stand in the right causal relation to the thermal spectrum of the wiggling and jiggling of the microconstituents of the horizon. Only then can one conclude that the temperature of the thermalized quantum radiation is a sound proxy for the temperature of the black hole itself, as determined by the dynamics of presumably its very own microdegrees of freedom. But it is exactly the lack of such bridging principles that I will argue, perhaps as we will see is too strong of a claim, as I will argue, calls into question the importance of the information loss paradox, calls into question the ability of the information loss paradox to teach us anything deep about what a theory of quantum gravity has to look like. So perhaps the derivations of Hawking radiation themselves, which don't depend on a coupling of the quantum field with classical geometry, that's exactly what the issue is here, are already trying to tell us not to take any of this terribly seriously with regard to fundamental issues. So this is just a restatement of the final state, paradox, dynamical evolution from pure to mixed states, biaxial unitarity. I'm not, in the interest of time, because Sakshi, I thought, did an excellent job presenting it. Dan has talked about it. I'm not going to describe the page curve problem in any detail. I'll just state the bare bones of it. So we treat the black hole as a statistical mechanical system of quantum degrees of freedom, just like any other quantum system. Then the emitted black body radiation will eventually no longer be thermal, because there must be entanglement between the early and the late time quanta in the radiation. But semi-classical gravity says Hawking radiation is thermal. Therefore, we get a contradiction between the statistical mechanical treatment and the quantum field theory treatment of black hole. And as Enrico asked, I think it was yesterday. God, I'm completely losing track of time. As Enrico asked in a previous lecture, and as I remarked, I completely endorsed, Pache Wallace, this is still, I think, fundamentally an issue about failure of unitarity. Because if unitarity were satisfied, then there wouldn't be this contradiction. So if you accept that, we have all of these arguments that unitarity in some form or other fails. All these arguments seem to me very prima facie strong. Why then are physicists so freaked out by the idea that we might lose unitarity in the case of black hole evaporation? And I think that this question is particularly poignant when one considers that these same physicists are not freaked out about loss of unitarity in standard treatments of other quantum fields and effective field theory formalism. And for that matter, they're not freaked out by seeming loss of unitarity in projective measurements in standard quantum theory, irrespective of what interpretation of quantum mechanics be like. What I mean by this, by the way, I probably should have spelled this out more in the slide. In standard effective field theory standard effective field theories in particle physics, when you construct an effective field theory, it's very common for unitarity to be violated in the effective field theory. And no one freaks out about it because we understand why it happens. In the effective field theory, as I'll explain in a moment, I'll explain why no one freaks out when it happens in ordinary cases of effective field theory and standard particle physics in a moment. Just know for the moment, it does happen all the time. No one worries about it, with good reason. And so correlatively, why do physicists feel confident that an effect predicted by what is manifestly an effective field theoretic calculation, because we're treating gravity classically and no one believes it's truly classical, why do physicists feel so confident that we can trust that a conclusion of an argument in this context reveals features of some underlying fundamental theory of quantum gravity. Because if they don't think that loss of unitarity in these arguments shows something about quantum gravity, why do they care? The only reason I can think they care is because they think that showing loss of unitarity here implies that unitarity must be lost at the quantum gravity level. I call this the cascade problem. Why assume failure of unitarity at the semi-classical level automatically cascades down to a failure of unitarity at a level of more fundamental theory of quantum gravity? Here's one plausible answer why people get Enzo, is that any question?
Erik, sorry,
Yes.
Vincenzo has a question
Yes.
for you.
Good.
Oh yes, but perhaps you are answering to my question. It was not. I agree a lot with your first point in the preceding slide. Why physicists that do not care about the loss of unitarity in quantum measurement problem are so worried about what happened in black holes. But I do not understand the nexus between the first point and the second point in that slide. You can come back to.
Yeah, I'm actually going to try to directly address that.
Okay.
Right now and in the next few slides. So the claim is in other standard effective field theory treatments of particle physics problems, but unitarity is violated. No one freaks out about it because it's well understood why it's violated. It's violated in part because of the approximations one makes in constructing the effective field theory. And so in those cases, no one would ever dream of assuming that the failure of unitarity in that effective field theory example reflects the possibility that unitarity is violated at the deeper, true fundamental standard model picture. So why is it that people seem to believe that in semi-classical case, which is in some sense must be an effective field theory because we're not treating the gravitational degrees of freedom as quantum? Why do people worry about loss of unitarity there? And the only reason I can come up with is because, and some of them explicitly say this, is because they seem to think that loss of unitarity there in this semi-classical case has implications for whether unitarity can hold at the fundamental level, at the more fundamental level of a real theory of quantum gravity. So here's one plausible answer, I think, why physicists care. Why physicists might think the cascade problem, as I call it, is a real problem. In the case of black hole evaporation, as I've argued, there is an articulated dynamical mechanism that directly yields violation of unitarity. There's a real physical mechanism that has to do with the properties of the causal structure of space-time that is directly responsible physically for the violation of unitarity. And this is in clear opposition to the case of standard effective field theoretic calculations in particle physics, where violation of unitarity is manifestly an artifact of the mathematical manipulations used to make the calculations tractable, used to build the effective theory in the first place. And the loss of unitarity there doesn't reflect or represent anything physical on our understanding. And this is also the same reason why I think physicists who freak out about loss of unitarity in semi-classical gravity don't worry about loss of unitarity in projective measurement in standard quantum mechanics. Because that, again, this is in standard classical gravity, we seem to have a case where there is a dynamical physical mechanism that leads to the unitary violation. Also, this happens, this loss of unitarity we expect will happen at arbitrarily low energies, really big, large black holes, where one expects the high energy gravitational modes one ignores in semi-classical gravity to be essentially non-existent. Moreover, as I've just to perhaps reiterate in a more emphatic way, the failure of unitarity here follows from the geometry of the classical space-time background rather than from the dynamics of the quantum field. In particular, it is global features of the large-scale structure of such spacetimes that are responsible for the failure of unitarity, And one can plausibly expect, moreover, that such global features should be insensitive to any effects due to a quantum theory of gravity near the evaporation point, as I've argued, since those effects are appropriately localized in a small space-time region around the evaporation point. And Martin's theorem, I claim, makes all of this precise. So in standard effective field theories and particle physics, the breakdown of unitarity is often heralded as the onset of new physics. When unitarity breaks down in effective field theory and particle physics, everyone thinks that means, this is where new physics is showing up. Now we need to build a new effective field theory to explain it. Here, and so there though, in effective field theory in particle physics, the onset of new physics, breakdown of unitarity, is always happens where at high energies. But that's not where the breakdown in the effective field theory description I claim happens here in semi-classical gravity. Rather, the breakdown comes when there's complexity in the causal structure of space-time. In other words, when there's high entropy, not high energy in the gravitational phenomenon. And that's what makes, I claim, the issue of trying to think of semi-classical gravity as an effective field theory very difficult, because what we're essentially the relevant physical property that one has to take account of in characterizing the regime of applicability of the effective field theory, where the effective field theory works, depends on entropy, not on energy. But again, so let's ask our question again. Semi-classical gravity is just an effective field theory. Why get fussed about problems in effective field theory? And I'm now going to spend, I'm not going to make it through all the lecture, but I think I can finish everything I want to say about effective field theories in the next 10 minutes. So I'll do that, and then I'll save the epistemological ruminations for the start of next lecture. So the effective field theory. So I'm now going to explain in a little more detail, not much, just crudely sketch, how effective field theories work in both condensed matter physics, where they actually originally arose, the concept originally came from, and in particle physics and quantum field theories, standard quantum field theories. So we have what we do when we construct an effective field theory is we have some phenomenon we're interested in studying at some characteristic energy length time scales. We call those the IR modes, the infrared modes, low energy. So we construct a representation that we know is approximative of the phenomena, using only the degrees of freedom that we think are dynamically relevant at these characteristic scales. And the way that we do that is the UV modes, the high energy modes, the modes we don't care, the high energy stuff that we don't care about, that we think is kind of dynamically irrelevant at these lower energy scales. We quote unquote integrate those modes out of our mathematical representation. And what that really means is we kind of average all those modes and turn them into a coupling constant, so that all the physical information that's relevant at the low energy scale is just encoded in this in a way that the low energy stuff is coupled to each other. And so all the relevant causal impact the high energy phenomena has on the low energy can be effectively represented to an amazingly good approximation by representing it as a constant that mediates an effective interaction at the low scales. And here's just a really simple example. I claim that that frictional motion, dissipated motion in Newtonian mechanics is an effective field theory in this sense. Think about a block on sliding with friction down a plane. It's in ordinary Newtonian mechanics. You treat that by assuming there's a coefficient. There's a coefficient of friction that governs how the kinetic energy is dissipated. That's as the block slides down the hill, slides down the slope. That coefficient of friction, what it really is it's encoding all the averaged effects of all the little intramolecular electrostatic interactions between the molecules of the block and the molecules of the plane it's sliding on. Because that's what's really happening at the micro level. You have all these, you have all the atoms and molecules in the, in the plane, and all the atoms and molecules in the block that's sliding down it. They're all, pretty close to each other. They don't exactly touch. But so there's a lot of electrostatic interaction between them. And it's that cumulative electrostatic interaction that causes, at the gross macroscopic level, this dissipation, this slowing down, this friction. But miraculously, at the macro level, we can ignore all the fine details of all those tiny little electrostatic interactions and just represent it to an amazingly good degree of approximation by just sticking in a number, the coefficient of friction, that tells you that that adds a velocity-dependent force term to Newton's second law representation of the block sliding down the plane. And it's exactly, in fact, when that approximation breaks down, when we can no longer treat the frictional coefficient as a constant, that new physics appears. When you have to change your Newtonian representation of a block sliding down the hill. When you have to take more fine-grained account of the tiny little electrostatic interactions between the molecules of the block and the molecules of the plane. So let's look more closely at how treating semi-classical gravity as an effective field theory may bear on the problems I've raised. So there are two possible ways of thinking about how to treat semi-classical gravity as an effective field theory. There's kind of effective field. There's the way of thinking about it as effective field theory. That's like the way these things are used in condensed matter physics. And we can try and think about it as an effective field theory in the way that we use those things in particle physics. So in the first case, we would try to think of the classical geometry as a coarse-grained environment that the quantum field is coupling to. We're coarse-graining over all the quantum degrees of the geometry of space-time geometry, and we're coupling that's what we're coupling to the quantum field. That's exactly what you do in condensed matter physics, say with treating phonons, little quantized excitations of sound waves in a fluid. You treat the fluid classically as being a coarse-grained environment, coarse-grained over all its real quantum degrees of freedom. So you turn that into you treat the fluid classically. The little quantized phonons traveling through the fluid couple, interact with these coarse-grained degrees of freedom, and you generically get, in fact, what's called Lindblad evolution. It's non-unitary evolution that's characteristic of open systems and other standard cases. That's one way I claim of trying to think about semi-classical gravity as an effective field theory. The other way, the particle physics way, is you take what I will call the TBD, gravitational degrees of freedom. The TBD stands in English for to be determined. We don't know what they are. There's presumably some micro quantum degrees of freedom that are relevant at the quantum gravity scale. We integrate those out. Those are the high energy modes that we integrate out and couple the result, which looks classical, to the quantum field. And again, whereas it's always the case in the condensed matter, that you always get non-unitary evolution eventually because of the Lindblad, the way Lindblad evolution works for open systems. It's not necessary that you get unitary violation in these kinds of cases, but it almost always happens. It's completely reasonably, it's expected, and it's completely reasonable when it does. So let's think about the coarse graining way of doing it in a little more detail. So we treat gravity as a free statistical mechanical system with micro degrees of freedom, presumably properties of some possibly perturbative quantum gravitational states, and we coarse grain. Curvature is a macro property that external systems couple with, like temperature and pressure for gases or fluid flow for the phonons. And loss of unitarity comes about for reasons similar to why we expect loss of retrodictability for classical systems interacting with dissipative, coarse-grained, or effectively integrated systems. Because since we've coarse-grained over the real degrees of freedom, we've wiped out information about the real detailed information about the initial conditions. Just like the box sliding down the incline with friction coming. Once the box sliding down with an incline comes to a stop, its forward evolution is deterministic. If I tell you the initial conditions, if I tell you its position and its velocity, and I know the frictional coefficient, I can tell you where it will stop. But once it's stopped, I can't tell you where it came from. That information has been wiped out. And this, I think, and I would actually really be curious. I mean, Manus is the real expert here on the gravity from thermodynamics programs of Ted and Padmanabhan. So I suspect that this way of thinking about semi-classical gravity's effective field theory might be related to what Ted and Padmanabhan are up to, but I would be curious to hear what Manus has to say about that. If Manus might just say that I'm totally crazy, which could happen. Or maybe he'll say it's totally right. We'll have to wait and see. The virtues of thinking about the thing that's semi-classical gravity in this way, as coarse graining, is they might clarify some conceptual muddles, but also might raise some new difficulties. So one, it might thinking of it this way might give us a hint for the origin of thermodynamical character of black holes when external quantum effects are taken into account. It might give us hints for ways to explain why the black holes obey thermodynamical relations in classical GR, at least formally, where these theorems of differential geometry come from. Any theory of gravity at the classical level must recapitulate, at least formally, such thermodynamical behavior as a minimal criterion of adequacy, if this were all right. It seems to dissolve the information loss paradox. It shows why loss of unitarity at semi-classical levels need not imply anything about dynamics at more fundamental levels. And again, retaining a predictability with loss of retrodictability is exactly what one has in black hole evaporation. I can tell you what the mixed state that this pure, if you give me the pure state, I can tell you what mixed state it'll evolve into. But once I'm at the mixed state, I can't tell you what pure state I came from. And that's exactly the kind of behavior we expect from these kinds of coarse-grained effective field theories. It may still provide us guidance in looking for quantum gravity. We look for gravitational microdegrees of freedom whose statistics give the kind of coarse-grained environment that's required to recover semi-classical gravity. One possible problem is that even if all of this is on the right track, it still doesn't seem to rule out the following possibility: that general relativity could be adequate in some regimes in which seeming thermodynamical nature of gravity is irrelevant, so the solar system, and yet still be inadequate in those regimes in which thermodynamical character of gravity is relevant. So it might in fact be the case that we should be trying to think about semi-classical gravity as effective field theory, but just not in the way that would allow us to recover both solar system and what we think happens in evaporating black holes. Another problem is if you want to really use this to explain the character of semi-classical gravity, why it is that classical Einstein tensor couples to expectation value of stress energy tensor, this doesn't seem to give you any explanation of that. And it's also really hard to see how on this picture why. So I'm going to ignore 8 because I didn't give you the background for 8. I meant to, but for the interest of time, I'm not going to mention the problem that I mentioned that number 8 talks about. And you can ask me during Q&A, or you can ask me during in Slack if you're curious about 8. So I think about 3 more minutes. I'm sorry, and I'll finish. So now let's think about the EFT as integrating out in the way that we think about it, more like a particle physics kind of program. So we treat the quantum field degrees of freedom as coupling with something like perturbative quantum gravitational degrees of freedom. We integrate out from the interaction the TBD gravitational degrees of freedom. And now we note that this coupling in semi-classical gravity between quantum field and gravity can't be with fundamental quantum gravity degrees of freedom, because we don't expect those to couple with gross macroscopic, relatively speaking, matter. The quantum field, the scalar field, that's gross matter compared to quantum gravity. And we don't expect that fundamental quantum gravity degrees of freedom will directly couple with ordinary quantum matter. If it did, that would have shown up in CERN by now. The standard model wouldn't work. Fundamental quantum gravity modes don't couple to standard model quantum fields, the degrees of freedom in standard model quantum fields. So whatever this coupling is, whatever these quantum degrees of freedom are that we're integrating out, they are not fundamental quantum gravity degrees of freedom. They must be something like perturbative quantum gravitational degrees of freedom. Now, in the interest of time, I'm not going to talk about the virtues and demerits of this method, although they're interesting. But I'd like to come back to them maybe someday. But I would like to mention the particular bearing this has on the page curve problem. The fact that I just mentioned, that if we think of semi-classical gravity in this way as an effective field theory, that the degrees of freedom that we're integrating out can't be fundamental quantum degrees of freedom, but they must be something like perturbative quantum gravity degrees of freedom. That has actually, I think, direct relevance on how to think about the page curve problem. Because the argument assumes that black hole microdegrees of freedom in statistical mechanical treatments are entangled with Hawking radiation. Hawking radiation is a macroscopic phenomenon. It's standard model physics. Black hole microdegrees of freedom presumably are of the form that the EFT integrates outer core strings over. Otherwise, it's hard to understand how semi-classical gravity can be the framework for black hole thermodynamics. But so because these black hole microdegrees of freedom can't be, if they're coupling to the standard model field of Hawking radiation, can't be, I claim, fundamental quantum gravity degrees of freedom, anything that page curve calculations show you shouldn't be taken as paradoxical. It shouldn't be taken as teaching us lessons about fundamental theory, because the page curve isn't calculated in a way that necessarily tells us anything about fundamental quantum gravity degrees of freedom. So I'll stop there.
Okay. The space for the question is open. Okay, Manus, please.
Thanks for this really wonderful talk. I thought it was outstanding. I think it was your best so far.
Well, I mean, that still could be, you realize, got criticism. If the previous talks really sucked, then saying that might anyway. I'll take the compliment. Thank you.
So I think you might be right about your coarse-grained interpretation of semi-classical gravity. At the moment, I don't really have much to say about it. I'd love to read a bit more in your slides. But about the final state problem, final state paradox, and the Morozov argument, it seems to me that you're implicitly assuming that quantum gravity is some local, it only kicks in at the Planck scale when you say that it only matters very close to the evaporation point, whereas almost all of the resolutions of the info paradox, like ER's EPR and recent developments with islands, suggest some kind of non-locality in quantum gravity, which should be taken into account also in this argument. I don't know how this would resolve the final state paradox and the issue between Martin's theorem and Morozov's argument, but my suspicion is that it is super important and that it will,
So I think you're exactly right, and that's, I mean, the fact that all the current popular attempts to resolve the paradox do involve this kind of non-locality is exactly what Dan was talking about yesterday, and I presume he's going to talk more about today. I hope he'll talk more about it today. I want to hear more about it. I suspect, no, I think you're exactly right. That, but I think though that, so when I was trying to be more judicious and careful in my claims about my criticisms of Morell's argument, remember, in my most careful claim, I wasn't claiming to show that Morell's argument was wrong. I was claiming to show that he needs a principled reason for ruling out these kinds of causal violations and the possible relevance of these causal violations, of these consequent causal violations. And one way that he might do that is exactly by giving a principled, compelling argument that the kind of locality I'm implicitly assuming fails. If they can give me a really compelling argument to that effect, then I probably would be convinced that my criticisms don't work. But I have not yet been convinced been convinced that they are giving me a non-question begging way to rule out these causality violations. So far, from what I can tell, both sides are in the position of more or less saying, I have a preferred way of thinking about these things, and my preferred way shows that your preferred way doesn't work. But nothing yet on either side, I think, really directly answers to what the other side is doing. They don't make enough contact yet for us to give a principled argument. My way of thinking about it is right, your way of thinking about it is wrong. And so that's why I can say, I don't think they're giving me a principled reason. What I really mean by saying that is they haven't given me a reason that kind of works in my way of thinking. But they can say this, you're exactly right, they can say the same thing about me. So
I agree with this. I think you should press the holographers on this issue because you really believe in the Morell argument.
Yeah, I plan to. No, I've had a few arguments with Aaron about it already, and he's basically pushing back on exactly the point that you're making, and I gave him exactly the response that I just made to you. And we're kind of at a stalemate, but maybe we can make some more progress.
It would be interesting to extend, the current developments on page curves to the final state paradox, because these are really different paradoxes, as you.
I think so. I really think that would be incredibly interesting.
Then another short comment was that it seems that in quantum gravity you would like to make a distinction between quantum gravitational degrees of freedom that are like the micro degrees of freedom of the metric of spacetime, and matter degrees of freedom. But I'm not sure that distinction will hold. I mean, certainly in string theory, that's not how it works.
And probably in loop quantum gravity, there are good indications in loop quantum gravity that it won't work that way either. I completely agree, but to me, that's just one more reason to think that that problems in semi-classical gravity aren't necessarily going to teach us anything about fundamental quantum gravity, because the problem arises in semi-classical gravity explicitly by treating the gravitational quantum modes and the degrees of freedom and the material degrees of freedom as cleanly separable. That's an absolutely essential ingredient in constructing the paradox. But as you say, we may not expect that to be true at a more fundamental level. So again, to me, that's just one more reason to be skeptical that these arguments tell us anything about the fundamental level. So I want to be a little more careful in what claim I'm making. I don't want to say that these arguments tell us nothing about the fundamental level, because in fact, what they do tell us is that we should be looking for fundamental degrees of freedom that give rise to this behavior in an appropriate effective field theory. So these problems can still guide us, I think, in trying to find the more fundamental theory, but they don't necessarily guide us in the way people seem to think. Well, loss of unitarity up here must mean loss of unitarity down there. That's not the right lesson, I think. The right lesson is, let's treat this as an effective field theory where unitarity is lost, and look for a fundamental theory where a good effective field theory description is such that unitarity is lost.
Mm-hmm. Okay, thanks.
And
Erik, thank you very much. This was a brilliant class, and I learned a whole bunch of stuff. So thank you.
Thank you. I'm really glad to hear that.
So I want to better understand Martin Lezour's theorem. And I can imagine the details, the technical details are complicated, but the outcome, the physical outcome, so to say, is fairly simple to understand, if I understood it correctly.
I think, yeah, it is.
The idea is only that you just leave out the boundary of the black hole, essentially, or essentially you leave out the boundary when you attempt to evolve a Cauchy surface up to the future null infinity. So you can't. I mean, you can't say what. Well, you have to exclude the boundary in order to predict the future. So the information loss paradox cannot. So, yeah. So I'm a bit lost. But is this idea right? Or that
you're on the right track. You're definitely on the right track. So the idea is that you want to lay down conditions. You want to try to capture in a mathematically precise way the idea that there is an event horizon, there is a region in space-time such that inside that region there are points, there are events that can't make causal contact with future null infinity. But you also want to want to capture the idea that that region only exists for a finite period of time as seen from the boundary. So you want to try to capture the idea that at early times, you have part of the quantum field is in this hidden region, and at later times, no part of the quantum field is in this hidden region. That's what the physical idea of black hole evaporation is supposed to have as an implication, and that's what the condition. That's what Martin's trying to capture. That's the physical idea Martin is trying to capture with his. With the technical conditions.
Yeah, I see, but his topological result, the idea of his theorem, is that unitarity is not applicable to the boundary. So you essentially you have to exclude I mean, if you go if you go back to the slide, it would be easier, but.
Well, so I should say that we have to be careful here. Wait, have I lost my, no, there it is, share screen. So what Martin's theorem doesn't directly tell us that we lose unitarity on the boundary.
Okay.
What I claim it tells us that the space-time is causally discontinuous. And now I claim in order to really show that this means that we can't have unitarity on the boundary, I think we have to prove this statement.
Yeah, I see that, but where is it discontinuous? So before you made this nice example with the strip that you remove, and that's how you. Where exactly is the strip that you remove?
Right. So it's discontinuous here. So at this point of the boundary, right, the chronological past to this point in the boundary right here is this entire strip of space-time. Now move just the tiniest bit forward into the future, and now the causal past of this point looks really different. The causal past includes this little truncated strip right here. And
okay, so the strip is essentially this similarity.
Yes. So causal past right there, this nice strip. Causal past a little bit to the future includes this little truncated thing that looks nothing like what happened before.
No, I got it. Okay, thanks.
Vincenzo?
Okay, thank you. before posing my question to Erik, I have to make an important declaration about the chair of the conference. Yesterday, a very authoritative national committee established that Pierluigi won a tenure track in the University of Urbino, and we are very, very happy of this decision. It's a very important moment in the history of our team.
Thanks a lot.
That's fantastic. Congratulations.
Yes.
Thanks.
Very, very well deserved.
Yeah. Thank you very much.
Thanks.
Okay. I have a couple of comments about your presentation. That was very, very interesting. My heart is completely with you about this interpretation of the paradox lost as a sort of statistical fluctuation that could be explained in a more complete theory with micro behavior, and this is only a coarse grain behavior that is still now not explained. But I would like to know something more about that. You quote this program by Jacobson, and Pama, another very strange.
Padmanabhan.
If you can say something about this program, one, first thing. Second thing is more general. I posted this question to you also in Slack, but yesterday you drank too much to answer to my question. I think, but it is a very general question. I think to the history of Bishop Berkeley and Newton. He make very good observation about Newton mechanics.
Absolutely, yeah.
Yes, but no one care about his observation about calculus, absolute space, and absolute time, because physics must go on in a certain sense, and only his observation, like Popper emphasized, his observation became again fashion at the end of 19th century, and where the point of departure of a relativistic revolution in a certain sense, and also a real answer to the problem raised by Berkeley in the calculus arrived only in the second half of the 19th century by Weierstrass. So it was very, and I think that as philosophers, our task is also to put the finger in the point where there is some conceptual problem. But I think that also that this activity must be very humble, because the great revolution of physics in modern time, from Galileo to Newton, was exactly a sort of abandonment of the rigor that characterized Archimedes' way to make physics, that characterized scholastic thinking, and in a certain sense, Galileo, Newton, all these people are also experimental physicists, and they abandon the rigor and they make physics without thinking too much. And this is very important for the advancement of physics. So in a certain sense, my feeling, but I cannot understand very well, is that what is happening in this new calculation about the black holes that attempt to put together the laws of unitarity by Hawking on one side and equivalence principle on the other side. This calculation proposed by Pennington and other scholars is an attempt to make new physics. And so even if there is a lot of things that are not very clear, probably it contains seeds for new physics, and so it must be independent from philosophical warring. I don't know, what do you think about this point? Thank you very much.
Okay. Thank you. That's a really, really great set of observations, and and questions. So in the interest of time, if you don't mind, I'm not going to talk about the Jacobson-Padmanabhan program because one, Manas knows much more about it than I do, and I would want him to talk about it, not me. And in any event, there's not much time left, and I know there's still more questions. So and the second set of questions and comments I think is much more directly relevant to the subject. So if you don't mind, I'll focus on those. So so I have to say I just completely agree with basically everything you said and with the spirit behind your question. And I think what I think is you're especially that you put your finger on a really important point, that there's a sense in which what Berkeley did was fantastic because it was exactly people like Berkeley, and Berkeley did an amazing job. People like Berkeley pointing out that the calculus in the 18th century really was, in fact, he was right. It really was logically inconsistent. And his arguments were, some of the prime motivators behind people like Cauchy and Weierstrass in the 19th century, finally making it logically consistent. And thereby doing it, in fact, they opened up whole new fields of mathematics. So yeah, so you're absolutely right that it is part of our job as philosophers to find conceptual problems, not in the spirit. So where I think Berkeley was wrong was in the spirit he was doing it. He was doing it to say, this is all bullshit. That I think is the wrong spirit. The right spirit is, here are some really serious conceptual problems. Let's try and straighten them out. And in doing, I bet we'll learn some really cool new stuff. And so that is, I think, that I think is the right way to think about the kinds of arguments I've been making, and which is exactly, I think, what Manu's very, very helpfully really pushed me to state more clearly that my arguments against Morel, for instance, and those kinds of arguments, I'm not trying to say this is all mistaken, this is all misguided, let's just forget about it. What I'm rather saying is I really, really, really want you guys to be able to develop a kind of argument that will show me why I don't need to worry about the things I'm worrying about. And if they can do, I suspect, if they do that, they will at the same time have made some real advances in our understanding of quantum gravity. And if they can't do that, that will also, I think, give us some real insight and illumination into quantum gravity. Either way, we win.
Oh, okay. Julius?
I mean, I just wanted to hey Erik, hi everyone. I just wanted to complain about the de Sitter boundary conditions in the context of Marolf argument. So in particular, the step where
Julius, you warm my heart.
I mean, so in particular, so if we do consider something like a black hole in an asymptotically de Sitter cosmological situation, quite a few interesting things happen because it's not obvious that Martin's theorem generalizes to those cases because we don't have scry plus, which is explicitly used in at least the statement that you used, I think. So that's one thing. And the second is, but also, I don't know how to run Marol's argument because in particular, I don't know how to think about the step where I perturb some operators on the boundary to form a black hole inside if I have the de Sitter type disconnected boundary to the past and the future. So that's a curious case. It's a confusing case to me. What do you think about it?
I think that's a really important point, and there are some real subtleties here. First of all, Martin's theorem is applicable both to the case with standard asymptotically flat null infinity and with ADS time-like null infinity. So Martin's theorem is applicable to both cases.
But I'm worried about de Sitter type.
Yeah, no, de Sitter type, it's, yeah, I don't understand at all how to apply anything like Martin's theorem to de Sitter. I don't think anyone does. But at least in the case of Morol's argument, Yeah, I don't understand how to run anything like Merle's argument into Sitter either, and I am 100% confident that Aaron would agree with me on that. But there is a way of running Merle's argument in asymptotically flat spacetime with null Scri plus, not with time like Scri plus. There, what you do is you put the observers on Scri minus and say that the observers are allowed, you talk about observers that are really, really close to spatial infinity on Scri minus, and they do stuff and create black holes in the center of space-time, and then observers on Scri close to spatial infinity can make the measurements and observe what happens, and you prove that information that there is the there's the appropriate unitary relations between the operators on Scri minus very close to spatial infinity and the operators on Scri plus very close to spatial infinity. And you run Merle's argument that way. And it's a much more subtle and complicated argument, but I think it's just as strong or as weak as the much simpler, cleaner argument with the ADS boundary.
Okay, we can obviously continue the discussion on Slack. I would like to thank Erik for his great lecture. And okay, the school will start at the 2:30 p.m.
No,
No, at 15.
15?
3 p.m.
Okay,
Yeah.
sorry. Yeah, sorry.
Wait, I'm sorry, can you repeat that? We're not starting at 2:30?
No, today we start at 15 p.m. At 3 p.m. Yeah.
At 3 p.m.
Yeah.
Cool.
Yeah, because we have Daniel. We have only Daniel lectures this afternoon, and then we have the Gong show at 5:30.
Oh, cool. Then,
so to make the times manageable with the East Coast, we have to.
Then I will have more time to go to Slack and try to respond to all the really interesting stuff that's on there. Cool.
Okay. Well, thanks again, and see you later.
Enjoy your lunch.
Enjoy your meal. Light.